Hey, thanks. First, let's start about who the Canadian Electricity Association is. Our members are the corporate utilities in Canada from coast to coast to coast. We have investor-owned companies, provincially owned, municipally owned. Some are vertically integrated. Some live in open market situations, deregulations. That's Alberta and Ontario. So we have a wide variety. And we're the authoritative voice of electricity in Canada. It says the future of Canada's electricity system. I'm really going to talk more about North America than just Canada. And my background is out of the industry, mainly in generation. I have over 37 years in electricity. That puts me at risk at being labeled a Doug. Anyone know what a Doug is? Dumb old utility guy? So you can make your own decision if I'm a dumb old utility guy at the end or not. Usually what I cover, most people don't think of me that way, but we'll see. So what's our starting point? And this, we sometimes forget about what's actually happening today and the progress that's being made today. So if you actually look at our electricity supply system today, and on a Canadian perspective, which we show there, is we are about 80% non-GHG emitting today. When you add 65% of renewable, which is mainly hydro with a bit of wind, and add that to the current nuclear generation. And we are slowly decarbonizing. So environmental regulation in Canada, there's a coal-fired electricity generation regulation that comes into effect in July 1st next year. In the end of 2019, a number of coal-fired plants in Alberta, Saskatchewan, New Brunswick will shut down. If Ontario hadn't phased out early, most of the Ontario fleet would be shut down by the end of 2019. Each coal-fired plant in Canada has a shutdown date by regulation unless they invest in carbon capture and storage. Currently, one carbon capture storage unit it's in commissioning now. And actually, a week from today, I'll be out in Regina for the official opening of the Boundary Dam 3 carbon capture and storage units. So going forward, once units hit somewhere between 45 and 50 years, if they don't have CCS, they will have to shut down. We're also seeing significant decarbonization in the U.S. Through EPA regulations, not the Clean Power Rule, and I'll get to that in a minute, but through existing regulation related to criteria air contaminants such as NOx, SO2, regional haze, toxins such as mercury. A lot of older coal-fired units are becoming uneconomic in terms of retrofit and are shutting down, typically being replaced by combined cycle gas turbine units. So again, the carbon intensity of the sector is declining. On the graph there, we are somewhat at risk, or not at risk, we're limited by how Stats Canada reports things. So from the Canadian, when you see conventional steam and combustion turbine, add them together, that's our fossil-based generation in Canada. 19%, a little under 10% is coal, probably 8% would be gas, and there's 1% of oil still burned in Newfoundland. At Holyrood, when Lower Churchill, the first phase, Muskrat Falls, comes online late 2017, that plant won't be required. So really the discussion tonight is not about whether to decarbonize, the question is at what rate. And what are the risks to that rate of decarbonization? I'll come back to that later. Interestingly enough, and you know, they say in comedy it's all about timing, in good presentation sometimes, effective presentation all about timing. I did not know exactly what John was going to cover today and the detail he'd go into, but interestingly enough, Vision 2050 and why we created it was actually inspired by that NREL study. And what he didn't show is that if you went on the website, no, it's still there, but they actually had a model where the dispatch of the entire U.S. network, whole system, hour by hour for the year 2050. So that's 8,760 hours of the year all there, simulated with various wind and daylight and other conditions. And it actually, again, from my Doug side, I found it fascinating just to watch that play out on the desktop. However, your first reaction is, well, how could you actually be 80% the U.S. renewable? And then a couple of key factors come out here. One is that between now and 2050, effectively the bulk of fossil and nuclear generation in North America, so Canada and the U.S., will pretty much be at the end of life at some point in that. So there will be a significant need for replacement generation. It has to be replaced with something. So it's an economic opportunity that could be a true economic opportunity. It has to be replaced. What's economic to replace that? Which the study goes into in some detail. But the other thing that really struck me is the changes and flows in the transmission system, the amount of investment that would be required in the transmission system to enable that, to make that happen, that all of a sudden, I don't think people had a clear picture of what it looked like, the amount of land required for wind, rooftops of solar, concentrated solar plants, utility-grade solar, tidal, offshore wind, all the other elements that would come into that, and the huge transmission system and the flows required. I don't think people had a picture of it. And typically when people talk about, well, we should take this action because the GDP impact is so small, when we talk about GDP impact, we tend to nationalize it, and maybe it doesn't look like a large impact. But when you actually see the changes in flows where facilities close and others open, the economic dislocation regionally and locally is a different story. And when you realize that people are impacted by that, and you realize that those people are voters, you understand the political challenge in making some of those decisions. So it really got us thinking in terms of it's a possible future. We'll never say that it's not. But if you understand how decisions get made and how the system evolves, how would we actually get there? And so we started thinking more about rather not what 2050 would look like, but what are the key factors that will lead to what 2050 looks like? And in fact, decisions that will be made in the next 10 to 15 years is pretty much going to determine what 2050 will look like because of the long-lived nature of the capital stock. You can only afford to invest so much. So decisions we are now will embark upon in, say, the next 10 or 15 years are quite critical to determining what 2050 will likely look like. So we came up with 4 key factors. First one is the customer. And it's within the electricity sector, we sometimes still refer to, quote, the good old days when between the utility and the regulator you determine what was in the best interest of the customer. Those days are slipping by. Some places maybe it's still there, but it's really changed. But technology is enabling the customer to be more involved in the system, whether it's in terms of energy efficiency, home energy management systems, when you charge your EV, and John mentioned some of those factors in there in terms of variable demand response, or whether you have a solar panel, or whether you have a microturbine and natural gas and a whole bunch of other technologies. But there's a whole area of innovation that's happening on the customer side of the meter that's changing things and improving energy efficiency. And we also have a new generation of customers growing up, and many of you here are that newer generation coming up when you become electricity customers. You've grown up with different technologies you're more familiar with. Maybe you want to get involved in the electricity system in a different way. You want to manage energy costs in a different way, or knowing that also relates to environmental impact. And you want to relate to your provider in a different way. So these are factors that are going to change the electricity industry significantly, both in terms of its business models and how it relates to the customer. Carbon, and what that comes down to is what practices or measures are we going to put in terms of dealing with carbon. And there are a variety that are out there. And what we do in the paper, we talk about the pros and cons of different ways of dealing with them, all the way from feed-in tariffs, net metering, investment tax credits, renewable portfolio standards. But we come to the conclusion that if we want to deal with carbon and optimize on that, then the only way to really deal with it is to price it in the economy, fully in the economy, and for electricity, minimum North American basis. We say minimum North American because of the impact. If you do it regionally, you can get significant carbon leakage. But electricity, it's hard for us to get it outside the continental borders. We're not at the point of loading up batteries and putting them on a ship to China or anything like that. And we haven't figured out how to transmit electricity other than through a wire, certainly large volumes. So whatever decisions are made, and I'll talk a bit more about what's happening in Canada and the US on that as well, will make a strong influence to what's achievable within some of the modeling that NREL did. Electric vehicles, and I am an EV owner, the Chevy Volt, so I speak from experience. The driver for EVs, no one's picked up on the joke, driver for EVs. Let's throw that one out. Anyways, but the customer angle for EVs argument is not an environmental one. It is for some people, but it's actually an economic one. They are much cheaper to own and operate, even at today's cost of vehicles and batteries. Within a large urban area, we're going to see more demand eventually, a customer pull, and that will be a factor because that actually will increase demand, but also, if done properly, ties into variable demand response. And the last point, it is a North American grid. We have 35 interconnections between Canada and the US. There's 6 more in various stages of permitting, 3 of them from this province. In 2013, trade was a net 53 terawatt hours electricity from Canada to the US. That was about 63 terawatt hours out, 10 terawatt hours in. Most of you won't really know what a terawatt hour is. It's 10% of our annual production ends up flowing south for the most part. What most people don't know, this is all based on economic transactions and the interaction of markets. So much of the trade is actually done on an hourly basis. So there are a number of wholesale markets in parts of the Northeast US, Ontario, Quebec is intertied with those. There's an interplay between all of them that leads with a net export into the US. And really, when you think about where we're already starting from in terms of a much less carbon-intense supply system, we're actually helping decarbonize the US system today, and there's significant opportunity to increase that. So let me get back to the rate of decarbonization, the factors and the risks that need to be considered. So we can start with a discussion on how much do we want to spend to increase the rate. So we're on a natural progression now, but if we want to increase it, how much do we want to spend on it? Ontario took the position of getting off coal as fast as possible. It took a very large amount of capital in a short period of time, and you know, the Green Energy Act Ontario gets blamed for the current price of electricity. It's really only appropriately blamed for the planned increases in the price of electricity in Ontario. Where we got to up until about a year or two ago was the large investments required to build gas plants or move gas plants. That's an Ontario joke. But to build gas plants, new transmission lines and other transmission upgrades, refurbishing nuclear plants, expanding hydro plants, tunnels, a whole bunch. A lot of money went in a short period of time that gave a very large rate increase. That was a known factor for the Ontario government. They consciously traded off the affordability aspect of electricity and the price impact with their sustainability objective. The U.S. EPA Clean Power Rule, which is now in the comment stage. It states state intensity targets for 2020 and 2030, and the targets are established by looking at 4 fundamental building blocks. Make existing coal units more efficient, and they target a 6% improvement rate. And that's mainly by turbine upgrades, newer technologies, and metallurgy. You can get a very 6% is not a big improvement. It's not insubstantial given the size of the fleet, but they've targeted 6%. Redispatch load so all the existing gas-fired units, dispatch them and load them up before you go to coal, so that's changing economic dispatch. Ironically, that makes existing coal fleet less efficient because they're most efficient at full output. They're less efficient at partial load. So I'm not sure in their modeling how they did that trade-off. Continue to invest in renewable energy generation. Most of the states have renewable portfolio standards. Keep the existing nuclear fleet in operation. And that's in a number of states that are open markets. There are a number of nuclear units. They're not sure how much longer they'll keep operating. They're economic, given especially a low gas price environment that really links into wholesale electricity prices. They're actually saying states should subsidize the ongoing operation and keep all nuclear units in service, as well as continuing their 5 units under construction right now in the U.S. So, and continue with energy efficiency programs. There's an aggressive target on energy efficiency. So that's how this target per state has been calculated for 49 states. Vermont's the only state without a target because they're not using the coal today or fossil today. So it's 49 targets. So the states have the flexibility to achieve the target in any which way they can. They don't have to use those same building blocks, but that's how it's created. I'll give the EPA credit. I mean, they have factored in capital stock turnover that, so they're not saying walk away from all coal. They're saying migrate, bias dispatch, keep doing other things, and over time, you'll get a reduced carbon intensity of the overall fleet. It also highlights some of the weaknesses in doing sector-by-sector regulation, which I know is Canadian government favorite, but it's really a suboptimal way to do, because we mentioned EVs. You increase the amount of EVs, and if you have even the intensity of a combined cycle gas turbine, it's a much better CO2 argument to have an electric vehicle than it is an internal combustion engine in a car. But you increase demand, and you can actually make it harder to achieve your state reduction targets, but even though you have reduced the CO2 intensity of the entire economy. So that's why sector by sector is not really good. So this is still a work in progress. There's still lots of court challenges to go through. I think it'd be very cumbersome to implement state by state because our electricity system is much broader than that. In a lot of cases, doesn't recognize state boundaries. Certainly it'd be a lot simpler to have an economy-wide carbon price. You know, so there is actual possibility that through the EPA ruling, assuming it holds up the court challenges, and the record's been pretty good the last 2 years, it becomes so cumbersome it calls for a legislative solution that will eventually get us to pricing carbon in the economy. So when I tell people I could see a carbon price in the U.S. by 2020, they all would laugh, and I said, no, here's how it could happen. Not saying it will, not going to predict, but in 2020, if there is one, remember you heard it here first. I've had people say, I remember you said that in 1999. I can't remember what I said in 1999, but I think one of the claims they said is we'll start to take climate change more seriously once the insurance industry wakes up, because it's an economic argument. I got that one right. One of the interesting things is the ongoing role of nuclear. Now, while the NREL study focuses on renewables, higher renewables, and a lot of people want to talk about renewables, the wild card through all this is nuclear. And both it plays a critical role in Ontario and New Brunswick and a few parts of the U.S. as well. It has a significant support role to support the stability of the grid. It's not easily replaced by other non-emitting supply, with exception in some cases of large-scale hydro, but the issue of how far can you transmit electricity. Down the road, maybe fusion has a role, and if I had heard myself say that a year ago, I would have laughed at myself. But actually, I visited with General Fusion in Burnaby, BC, and their approach, which is different, mainly privately investor funded as opposed to just government programs. It's not as far-fetched as I once thought, but it's certainly not a technology for 10 years. I'm not sure if it's 20 or 30, but down the road, fusion might be. And fusion, the way it's been contemplated, actually would be a renewable technology, which is another lesson here. We're thinking renewable, solar, tidal, wind. It's not the only way. And there are other technologies. Technology is never static. So what about renewables? Distributed generation, energy efficiency, and storage, and it can go on and on and on. In the end, we must remember the decision-making process on an evolving grid is based on balancing three key attributes, and it always keeps coming back to this: sustainability, affordability, and reliability. Now, if you go by the way the grid grew, I mean, sustainability is part of a recent, say, the last 30 years, it's become, we've talked more about it. Prior to that, it was all about reliability and affordability, but now sustainability and sustainability objectives. So sustainability, from our perspective, really is the move to non-emitting and renewable sources, as well as minimizing the environmental impact of all technologies, because we might be addressing, from a climate perspective and a renewable perspective, it doesn't mean there's zero environmental perspective. Land use issues, whether it's hydro, solar, wind, there are a bunch of other things that come in. It's not just about air emissions. In terms of affordability, it's an interesting discussion. When we talk about the amount of investment required in the electricity system for renewable modernization, people say, oh, we can't have prices going up. Well, if you focus just on the cents per kilowatt hour, then it's probably not the best way to look at it. And we more look at it in terms of what do you spend in dollars per day, and how does that compare to other things you need to live, whether it's telecom, food, clothing, housing, and electricity. Canada and the U.S., regardless of what province you're in, typically it's about 2% of household spend. And when you actually look at, if we want to focus on dollars per day and what we're spending, so even as electricity price in cents per kilowatt hour goes up, because of improving energy efficiency and opportunities, whether it's the capital investment to move to LED lighting, or the car you drive, energy efficiency of appliances, whatnot, doesn't mean your actual daily spend has to go up as fast. But certainly we do expect the price in cents per kilowatt hour will be going up faster than the rate of inflation. Reliability. When you actually talk to most people, it's certainly done a lot of focus group work that, and I've seen it in Canada and the U.S. in surveys. Reliability is what we value most. Now, we don't often say it in that way because we don't think in those terms, but what is our expectation? You flip the switch, a light goes on. There is no other business anywhere in the world that meets a customer demand as fast as electricity. Moves at the speed of light. It's there, it's instantaneous. And when that instantaneous reaction happens, something happens in the system. It's not like you can wait for your cell phone if you have a drop call. If you have drop calls, or if you have delays, or you get that little stupid circle on your computer going around and around and around and around while you wait, you can't manage that in electricity. You can't live with that. So reliability is very important. And the complexity of the system is really hidden from the public. How do you balance it? Now, the NREL study, when you go into all those moving parts, you start to get a sense of how complicated and complex the system is. And certainly moving to a more renewable system makes it more complex. However, technology is enabling us to manage that as well, which is a critical part. But when we talk about generating electricity, we talk about whether it's kilowatts, megawatts, gigawatts, and kilowatt hours, megawatt hours, gigawatt hours, terawatt hours. We think in capacity and energy in those terms, but there are critical reliability services that are required the system provides today. Frequency control, voltage control, inertia to start large motors, ramping service. Those are all critical physical elements required in the system to maintain reliability. When we had very low penetration of solar or other technologies, it didn't really matter that much. As we see higher penetrations, we start to see reliability issues. And Hawaii is a significant example of that. So one of the really good papers that's been done in the last year is the Electric Power Research Institute paper on the integrated grid. Was released back in February or March. And it really does an exceptional job of breaking all these things out. Not to say we can't have that future, but to say here are the technical issues that we have to deal in order to have that future, which is similar to what NREL was doing. It says, if you want that, here are the things we have to deal with, and there's a whole bunch of technology issues. And technology issues that people are dealing with. There's some people that say that we should move quickly to a large renewable electricity supply system. There are others that say it's not possible. I would never give up on what technology can deliver. But there's one more aspect to this. It's not just what technology we need. It's actually the commercial and business models and regulatory systems that enable our use of technology that really can make it happen. And that is sometimes more of a challenge to get around because we have opportunities with certain technologies, but we don't have the commercial models in place to really make effective use of them and to optimize the use of technology. Now, when going through and preparing for this, I thought some questions might come up that I'd need some other slides, but I think I'll go into them anyways just to explain. So here's a physics lesson, and being an engineer, I like going back to physics. I like the laws of physics. I actually know what they are. Everyone knows what they are. Everyone has the same understanding of what they are. Supreme Court can't overturn them. Politicians can't get around them. So here is a true issue from physics that the solar industry in the U.S. likes to promote. You put a solar panel on your roof, you're going off grid. Well, you're not. You're still connected. And in fact, if they were off grid, their air conditioner couldn't start. And that's because of the inrush current of your the motor for your air conditioner requires much more than what your array can provide, and actually your whole system would just trip and shut down. Now, motor starting technology changes. It'll have to change to handle that, and smart inverters are required, and they're coming. Part of the challenge from a technology is that a lot of how the system works today in reliability services have always been provided by large rotating masses. If you go to more digital supply, then you need power electronics to replicate what we have had from large rotating masses, and that's technology all effectively in development. My other favorite one, I'm glad you didn't use the Sankey diagram. And I can usually spend hours on these things, but according to Wikipedia, the Sankey, it's named after an Irish captain, Matthew Henry Phineas Riel Sankey, who used it in 1898 to show the energy efficiency of a steam engine. This is the U.S. system estimate from 2013. I find the Canadian one has, to me, some sort of flaws in it. They're not wrong, but it's just their presentation is not as good as this, nor is it's not as up to date. There are a lot of things we can get from this. On the far left are energy inputs. This is for the energy, not just electricity, whole system. And on the right, very far right, we have, I don't know, is this a pointer? Anyway, we have energy services and rejected energy. I like rejected energy because it goes back to any engineers in here that have thermodynamics. No useful work or energy is from heat in minus rejected energy is useful work energy. So it's a term from physics. And the fact that the rejected energy box is so much bigger than the energy services box is not just that we're all inefficient and we leave the lights on. A lot of it is reflecting thermodynamics and limits of the technologies we're using today. So when we look at electricity, so let's look at a couple boxes. So you see the ratio of 12.4 useful energy out. You can see a little bit of the imports from Canada at the top. And then the rejected 25.8. And these are in quads, which I guess quadrillion BTUs. So that's an average efficiency of 32.5%. So if you actually look at the efficiency of generation technologies, subcritical coal units about 35%, supercritical low 40s, combined cycle gas say mid 50s, nuclear is about 30, all limits of thermodynamics. What most people don't understand, anyone know what the efficiency of a solar panel is? If you look at the total potential energy from light hitting a solar panel to the output from the inverter, 17%. That'd be a good system. So when you actually look at the challenges of solar, and gave the speech to solar industry once, he said, I'd be focusing more on getting your efficiency of the panel, and I don't know what not knowing that side of physics and light, I'm not sure what the limitations or how efficient a panel can get. But you imagine if you took the 17 to 34, how much more energy you could get from a roof, or how many fewer roofs you would require from solar tops. So it's that lack of efficiency and something that's very lack of density of energy to start with is an issue. In Canada, if we show the Canada one, because we have so much hydro, our electricity numbers look a lot better. So US, I've calculated it's about 32.5%. Canada, it's over 55%. And that's because hydroelectric average efficiency is 85% plus in terms of conversion efficiency. Ironically, our one of the biggest and oldest technologies we use remains the most efficient one we have. And if you could look at solar, you see the light yellow lines are hard to see. But if you actually look at the numbers, not the relative size of boxes, you see how small solar makes in 2013 to the overall U.S. energy system. So when I talked to the solar people, said if you're an optimist in the solar business, a lot of upside potential. But you can also understand that if you're sort of based in the other business, say how can that ever seriously compete? You know, and neither do you, well, I shouldn't say the solar one, I would be optimistic in the long run, but that idea that it can't compete is wrong. But it just gives you the magnitude of the challenge to be dealt with in the energy system, how big it is and how much is required. So when someone says, you know, we could all move to solar and wind tomorrow, you realize, oh, really? It is an evolution. This whole system has evolved over time. No one sat down and designed it. It's just what's evolved. And it's interesting the way it's evolved. There's something else about technology in here. Because the way it has, the challenge of wind and solar is it has very low energy density. So if you measure the amount of energy per unit area or unit volume or mass, depending on the fuel source you're talking, the energy density is quite low. Nuclear, which is still a large chunk, is the complete opposite end. You can't get anything more dense than that from an energy density. So what are the technology problems? Well, with wind, the lack of density is a technology problem in harnessing. We talked about the panels and efficiency of and size of wind turbines. On the nuclear side, the cost to manage that dense energy source was not foreseen, at least does not appear to have been foreseen, when we started planning this as part of our energy system back in the late 40s and through the 50s. Its density was extremely attractive. It was considered low waste, cheap, you don't need a lot, but the fact of the challenge in managing the public safety issues around managing radiation and all that, and the huge support systems required to keep it safe has cost a lot of money and has changed the economic argument for it. Which leaves us with natural gas, coal, and oil, which is sort of right in the middle. Good energy density, easy to transport, economic to transport, and we had lots of technologies to deal with them. So that's why we have the system we have, and that's why we talk about evolving to something different, and that's why it takes time to do it. The other area to look at is the four key use boxes: residential, commercial, industrial, and transportation. And what really screams out in that one is, you know, residential, commercial, industrial are relatively efficient. Transportation, look at the waste. Just look at that. That's because of limitation internal combustion engine, 30% efficient. That's physics again. And that's again why the argument for electric vehicles in the long run is an economic one as well, environment one. You can reduce the rate. And also when you look at that, if you can see the impact if you improve efficiency in the technologies that make us more efficient in that area and how it relates back to shrinking what you need on the other side. And that's why energy efficiency programs are so important. Okay, last thing to cover. We talked a little bit about EVs, EV charging, commercial system. Variable demand response. There are a lot of opportunities there. But I'll end with energy services and a notion about energy services you need to think about. When you sit down, do you think I want electricity, I want gas, I want gasoline, oil, that? Not really. What do you want? You want a motive force, you want light, you want heat. So the more we think about in terms of the energy services required and how we manage that, impacts on the storage side. So a lot of people would say, well, if we have more battery storage or flywheels, we can manage a lot of the wind issues or the variability of wind and solar. And yeah, some of that you can, and with large hydro it really works well with wind. But in reality, we also need to start thinking that what we really want is, why not have storage in the form of the energy service that we want? And that goes back to, John did mention the ice storage, and I actually was involved in building a small district energy plant in Windsor. It supplies the casino down there. Ontario Hydro did it with a company out of Chicago, and we made ice off-peak when electricity prices are quite low, and then melted the ice during the day. So the chillers only ran at night to make ice. So we had thermal storage. Really good balancing out the demand and supply in the system, and shaves the peak in the day and fills the valley, and that's what you want for efficient dispatch. That was 1995, 1996, built that. It's been around. There's a fair amount of district ice chilling there's some in Boston, Chicago, Las Vegas, a few other places. Another one would be Power Shift Atlantic that MB Power is at the forefront of, along with PEI, Nova Scotia, and the Natural Resources Canada is involved. But that's looking at electric storage heaters, hot water heating or home heating, and have that demand respond to when the wind blows. So what you want is heat. Doesn't really matter. The internal temperature of the heater could be within a wide variety, and you can still get the heat you want, but have that heating element come on when the wind blows. And having that variable demand response balance in the system is just another tool that's being developed in order to balance out and make it. But the advantage of storing it in the heat system you want is, each time there's a transformation from electricity to an energy form back to electricity, to loss of efficiency. So if we want to get this box all squished in nicely, we have to think about how we do energy storage. And I think with that, I've covered the most part, and we can turn it over to questions then.